Hello, my name is Magnus Petersen. This video is about a new Python API for downloading and working with financial data. The API is incredibly easy to use and a lot of the data is currently free. This API is a game changer in how financial research can be made and shared with others. In this video, I will show you the basics of using the API, as well as a few example applications, including machine learning and neural networks. Let me first give you a brief background story why this is important. Just a decade ago, you had to pay $10,000 to $20,000 to get access to a professional financial database if you wanted to work with large financial datasets. Then companies in the United States were required by law to start filing their financial reports in a so-called XBRL format that could be crawled more easily by computers. This has given rise to several discount data providers who have a basic web API for getting access to the data. But those web APIs still require that you implement a lot of logistics for downloading and assembling the data, storing the data in a local database, and finally loading and processing the data. The Symfin API makes this much easier, as it handles all of the logistics for you, so you can start working on the financial data with just a few lines of Python code. Moreover, you can very easily share your research with other people through Python notebooks, so other people can run the exact same experiments on their own computer or even in the cloud using, for example, Google Colab. It is my hope that other API providers will get inspired by this, so we can see a lot of innovation in financial data APIs in the future. And I hope that this will lead to real progress in financial research. Because currently it is only the leading hedge funds who have been able to make real scientific discoveries about how the financial markets work, and the hedge funds use that knowledge to make themselves extremely rich, but they don't share their knowledge with the rest of us. On the other hand, we have academia, who are supposed to make scientific discoveries for the benefit of all mankind, but in reality, academia is usually more about the egos of the professors than the pursuit of truth and science. The result is that academic finance is still in the dark ages. And this brings me to the reason why I have this photo of Salvador Dalí, who was a very famous surreal painter from Spain. Legend has it that Salvador Dalí refused to take the exam at the art school he attended because he did not feel that his teachers were competent enough to judge his work. So they threw him out of the school. My question to you is whether you can name this school or any of his teachers. No? Well, that's exactly my point. Salvador Dalí and his work will live on forever, but nobody knows who his teachers were or even the school he attended. It is my hope that somebody out there will use this financial data in new and innovative ways to make proper scientific discoveries about how the financial markets really work, so the markets can hopefully become more stabilized in the future for the benefit of everyone. I hope this dataset and beautiful Python API can help turn one of you into a Salvador Dalí of finance, because groundbreaking discoveries will certainly not be coming from academia. So let's get started. This is the Symfin website. Some parts of the website are currently being redesigned, so by the time you see this, it might look slightly differently. But the page that we are interested in is called Bulk Data. And here you can select all of the datasets that are available. So for example, we have balance sheets, cash flow statements, income statements, share prices, and various other datasets. We will take the income statements as an example. And here you can also select which market. Currently, the database only has a little data from Germany, and it has quite a lot of data for the United States, so we will keep it at that. Some of the datasets you can also select a variant, and for the income statement, we can select whether it should be annual data, quarterly data, or the trailing 12 months. So this will have 4 data points per year, where each data point covers the last 12 months from that point in time. For some of the datasets, you can also select the details, whether it should be normal or full. So for example, in the case of the income statements, the full dataset will have more data columns with more details. And if we click it, you will see that the table below changes slightly, like so, because now there are many more data columns. You will note that it says Symfin Plus only. This means that it requires a paid subscription. It is not very expensive. You will also note this line here, which says that the selected free dataset is delayed by 12 months. And again, you need to upgrade to Symfin Plus to get the most recent data. So if we go back to the normal one, we can click Download CSV file. This downloads a zip file, which has a text file inside with comma-separated values. This file can be loaded in a spreadsheet, and you can see if I click it, it downloads the file to my disk. And if we double-click it, it will open in my spreadsheet, and then we import it. And then you have all of the data here. And you can see there are thousands and thousands of rows of annual income statements for companies in the United States. And this data is all free. I wasn't logged into the Symfin website when I clicked this button. Everybody can get this data. But it is currently delayed 12 months because we need to give an incentive for you to actually pay for the data so we can get enough revenue to fund future development of Symfin, hire more people to check that the data is correct, and also add features to the Python API. So if you want to buy an API key so you can get all of the fresh data, the complete datasets, you need to click on the link for Symfin Plus and buy a subscription. And it's not expensive. Even if you only play around with the free data for a few days, then buy a cheap monthly subscription to help the project. So let's look a little more at this table, what it actually shows. It shows the column name for the data, revenue, cost of revenue, gross profit, operating expenses, and so on. Then it shows the Python shortcuts, and we will get back to these in a moment. Often there's only one. Sometimes there's two, like for operating expenses, or selling, general and administrative. And here in the last column, we have the data coverage, which means how many of the rows in the dataset actually have a data value here. So we can see that 98% of the rows have the revenue, only 91% of them have cost of revenue, and so on and so forth. Eventually, there should be a question mark icon next to each of these column names, like we have an icon up here, and we have it down here for the share counts. And this will explain what each data column means. And hopefully, by the time you see this, some months in the future or whenever, a lot of these will have that explanation. Finally, we have some statistics for the free data and for the Symfin Plus paid version. So it has the file size of the zip file that you're downloading, when that file was updated on the server, and the number of data rows in this file. Let's go back up. Next to the button for downloading the CSV file, there's another button for the Python code. And if we click this, we get a little code example. And after you have installed the Symfin Python package, you can take this text here, put it in a Python source code file, and run it. And this will automatically download the data from the server, and it will print the first few rows of the data. And for convenience, it also gives you a one-liner if you just need the single function call for downloading this data and loading it into a pandas data frame. Let's now go to the GitHub repository where the source code for the Symfin package can be found. Again, we have a short example on how to use the Symfin package. I will explain in a moment what all of this is doing, so there's no need for you to pause the video now. All of this will become clear in a moment. But this short example here simply downloads the annual income statement for United States and prints the revenue and net income for Microsoft. And the output looks like this. That's how easy it is. If instead you want to load the share prices, it is this line here, and this line here plots it. So we get this image here. Again, that's how easy it is to work with the Symfin package. But it can do a lot more than this. Before we start looking at the tutorials, let's just take a brief look at the documentation for all of the public Python functions in the Symfin package. For example, let's see the chapter on loading data. We have that here. So first, there is a brief explanation of what this is about. And then there's a small note that the most important functions can be called directly from the Symfin namespace. So for example, instead of calling symfin.load.loadIncome, you can simply call symfin.loadIncome. Here we have the basic load function, and I will explain this in much more detail in a moment. And apart from the documentation of the function, you also have a link up here to the source code on GitHub. So if we click that, it takes us right to the actual implementation. so you can see exactly what the function is doing if you don't think that the documentation is clear enough. One thing to note here is the special syntax sometimes used in the comments, and this is for the so-called Sphinx documentation system, which creates all of this here. And it's actually a really, really cool system, because whenever we push something to the GitHub repo, it automatically updates the documentation. And the special syntax that you just saw is for making these links here, so it can take us to another function, like so. So now let's go to the other GitHub repository for the Symfin tutorials. At the top we have an icon here, because every single day the datasets are updated on the server, and when that has finished, it automatically runs tests to see if all of the notebooks are working. If someday this says that it is failing, it doesn't necessarily mean that the whole system is failing. It might just be one single line out of thousands of code lines. At the moment, we have 10 tutorials, and these take quite a while to make. So if you like to see more, you really should pay for a subscription to help fund this development. So there are basically two kinds of tutorials. The first 6 tutorials has to do with how to use the system. Simply downloading the data is easy enough, but the other tutorials that we will go through in a moment teach you how to do things like resampling the data, how to calculate, for example, sales growth and stock returns, how to create signals such as valuation ratios, PE ratios, price to sales ratios, return on equity, net profit margin, and so on. And we are using what is called pandas, which is the standard for doing calculations on time series in Python. But pandas is not always easy or intuitive to use. That is why we have these tutorials, because this actually takes a long time to figure out how to do correctly. Then we have a tutorial on what we call data hubs, which is an even easier way to loading and processing the data. And this is what you will be using most of the time. You won't be using the basic load functions directly most of the time. You will be using the data hubs. Then we have a few tips on how to improve performance. And then we have the applications. First, we have a simple stock screener. Then we have basic statistical analysis. Then we have an example of how to do machine learning using scikit-learn. And finally, we have an example of making neural networks using TensorFlow and Keras. If you want to get really quickly started, I would recommend that you check out tutorial number 7 on the stock screener first. But if you are new to using pandas and financial data, I would strongly recommend that you take the time to go through and experiment with all of these tutorials up here, because you will learn a lot and you will avoid doing things the wrong way. So where can you run these tutorials? You can either run them on your own computer. This requires that you have Python installed, you need to have Git installed, you need to have pip installed. If you don't have a lot of experience with that, then I would suggest that you run it in the cloud first. You do that by clicking a link here, and that has opened another tab that we will switch to in a moment. But first we scroll down where it says Run in Google Colab, because there are a few things you need to do. At the top of the notebook on Google Colab, you need to run this line here, which installs the Symfin package on Google Colab. That might be sufficient for running several of the tutorials. If it isn't, then you need to copy and paste this code here and run it at the top of the notebook. So let's switch over to Google Colab, and we can see the entire notebook, but we cannot run it unless we sign in. So you have to sign in with your Google account that you use for Google Mail or YouTube or whatever. Once you have done that, you can run all of this in the cloud using Google Colab. So you don't need to install anything on your own computer. If you haven't tried this before, I recommend that you see some other YouTube tutorials on how to use notebooks and Google Colab and so on. It will be too much if I have to do a tutorial on that here as well. But basically, you need to insert a cell by clicking here, and then you copy paste the code for installing the Symfin package, or the longer code if that is necessary. And then you can say run all, and it should run the entire notebook. So this will download all of the data in the notebook to one of Google's servers in the cloud and run all of this code. That is pretty cool. So now let's actually see the contents of some of these tutorials, and I will show you this running on my own computer. So I open it, and we have it here. This is the first tutorial on the basics of how to use Symfin, what it is, what it can do, how to use it, and so on. So let's go through this and explain some of the basics of using the Symfin package. Assuming you have already installed it, now we need to import it. And then we have a line here for importing column names or shortcuts for the columns, and that will be explained in just a moment. Then you have to set a data directory where all of the data will be stored on your hard disk. Then you can set an API key, and if you use the key free, then it will get you the free datasets. And if the dataset or the variant requires a paid subscription, the server will generate an error. In a lot of the tutorials, you will often see that we are using this line here instead. This loads the API key from a text file on your hard disk, and if it cannot find it, then it defaults to the free key. This is particularly useful if you want to share your research so you don't reveal your own API key. But one of the great things about this Symfin package, and that a lot of the data is actually free, is that you can create research in a notebook like we're doing here, and you can share it with the world, and everybody can also run that notebook without having to pay for the data first. It is only if they want fresh data and the full data set that they have to pay for a subscription. So anyway, let's get to the general load function. This is a basic function for loading datasets, and the syntax is like this. So it takes a dataset name, a variant, and a market. For example, we are interested in income statements, and we want the annual income statements, and we want for the United States. If the file already exists on disk, then it is just loaded from disk, unless it is too old, or if the file doesn't exist, then it is downloaded from the server, then saved to disk for future use, and then loaded into a pandas data frame, where the first 5 rows look like this. And it has more columns. And if you get the Symfin Plus subscription, you get even more columns with more detailed data. And you can instruct the load function how often it should refresh the data on the disk by passing the argument refresh days. So if the data is older than this number here, it will automatically download new data from the Symfin server and load that for you. If you set this number to 0, it will force a download no matter how old the data is on your disk. And if you go from the free data to the paid subscription, you should do this. You need to either refresh it by setting this number to 0, or you need to delete the data directory on your hard disk in order to get the full data that you have paid for. So once you have the data loaded into what is called a pandas data frame, you can get a column of data using its full name. This is a little tricky because some of the names are really long. And if you have tried to use Compustat or other data providers, you will see that they often have very short codes for this that are really hard to decipher. The reason it is a good idea to have the full names is that when you do statistics and plots and so on, you actually get the full name. You don't get a weird little code that only a few people understands. Everybody can understand that this is selling, general, and administrative. But it is difficult to use in practice because you have to type this all the time when you want to address this column. So we are using what is called a shortcut, which is basically just a variable or a constant. And some of these are more descriptive than others. This one is a short code, but once you have seen it a couple of times, you will remember it. So SG&A is short for selling, general, and administrative. So if we use that to address a column, we get the same column as before, because it's really just a string with the full name of that column. And we can go back to the Symfin website here, and you can see a list of all of the different data columns. So we have it here, and the different Python shortcuts that you can use instead. So in this case, it has selling, gen, admin, or just SGA. So let's go back to the tutorial. When you use the basic load function, there is no index in the data frame. If we go back up, we see that the index here is just an integer 0, 1, 2, 3, and so forth. You can't really use that for very much. If you want to look up a specific company using either the ticker or the unique Symfin ID, then it needs to be indexed first. And you can do that in the load function by passing another argument here. So this will create a pandas data frame with a so-called multi-index for the ticker and the report date. Furthermore, we can instruct the load function that it must pass the dates for the columns report date and publish date, so that they become proper date formats in the pandas data frame. So when we do that, we get a pandas data frame with a multi-index for both the ticker and the report date, as you can see here. What this allows us to do is that we can look up data for a specific ticker. For example, if we are interested in Microsoft, which has the ticker MSFT, we get all of its data using this command here, and this gives us the data frame here with all of the Microsoft data. So it's very easy. If we are then interested in a specific column, we can simply add that to the end here, for example, for revenue. So first we get the data from Microsoft, and from that data, we take only the revenue column. There is a better way of writing this, and it will produce the same result, but it will only use a single lookup in the original data frame instead of 2 successive lookups. But anyway, if we want to plot the revenue, we simply add the instruction to plot it like so. So that was the basic load function. For all of the data sets, we have a specialized load function, so you don't have to specify which columns you want to use as an index and which columns have dates that need to be passed properly, and so on. For example, we have already seen this function here, sf.loadIncome. So it basically just specializes the basic load function by setting the parameter dataset to the string income, and then the index and the pass dates and so on. And if you want to index it by other columns, you just override that argument when you call this function. But when we call this function as it is here, we get this pandas data frame here as we expect. And similarly, there are specialized functions for loading balance sheets, which look like this. And you can see all of the first columns are basically the same, but the rest of the columns are specific for the balance sheets. And if we go back to the Simfin website, you can get an overview of the contents here. So cash, cash equivalents, and short-term investments. The shortcut is like this, and so on and so forth. And if we go back to the tutorial, we have another function for loading cash flows, and so on. So there is a difference between the date of the report and the date that the report was actually published and made available to the public. Currently, the way that the Simfin database works is that it gives you the newest data, because sometimes the companies will restate their financial reports, and this can happen several years later. Typically, what I do is that I use the report date, but in order to simulate that it has been delayed a few months because it's not made available immediately to the general public, I use a function in the Simfin API that lets me very easily add a few months to that date. That's what I do, and I'll get back to that in just a moment. But let's say that you want to use the publish date instead of the report date. As I hinted at above, all you have to do is to pass another argument for the index to the load income function. And then you will see that the multi-index is now the ticker and the publish date instead of the ticker and the report date. And what I prefer to do instead of using the publish date, because that can be several years later if the financial statements have been restated several years later. So if you want to use the financial data to calculate like price to earnings ratios, price to sales ratios, and so on, what I recommend you do instead of using the publish date is to use the report date, but add a few months. This could be 2 months or 3 months, depending on how conservative you want to be. So there is a helper function for doing that, and it looks like this. In this example, it adds 90 days to the index for the report date. But as I said before, I recommend that you use what is called a data hub or a stock hub, and this can do this automatically for you. And we will get back to that in a moment. So let's look at another argument to the load functions, and this is the variant keyword here. This depends on which data set that you are loading. For the income statements, you can either have annual, quarterly, or TTM for trailing 12 months. Banks and insurance companies are quite different in their financial statements than ordinary companies like, say, Coca-Cola or Microsoft. And in order to faithfully represent their financial statements, they have their own special data sets in the Simfin database. For example, if you want to load the income statements for banks, you call this function here. And again, it takes a variant, either annual, quarterly, or TTM, but this will give you the specialized data for banks. And this will have some columns here that are not in the columns for the ordinary companies. And there's another function for insurance companies. So now let's look at the difference between free and full datasets. And as I explained previously, what we mean by full datasets is that they have more data columns with more details. And in order to get those, you need to pay for a subscription. So for example, we can see the difference between the normal dataset, which is loaded with this function here, or the full variant, which is loaded by simply changing the variant name here to annual-full. Then we can calculate the difference to see which extra columns are in the full dataset. And the stats are down here. Number of columns in the normal dataset is 25, and number of columns in the full dataset is 66. So you get a lot more details in the paid datasets, but notice that not all of these may have data for every single row in the dataset. And then there's a long list of all the ones that are in the full dataset, but not in the standard one. Okay, so here we have the function for loading share prices. And here we have two variants, either the latest, so this is from the last day, or it is daily data points for several years. So for example, the latest share prices look like this. We have a row for each ticker, and then the date of that data point. And if instead we load the daily share prices by setting the variant keyword to daily, then you see that we have many data points for each ticker, one for each trading day. And this is basically the standard data that you find everywhere. It has the open price, the lowest price, the highest price, and the closing price, and the adjusted close, and the dividend and the volume. All of these numbers are adjusted for stock splits, and the adjusted close is really what is called the total return. But these columns are named the standard names that you will find on Yahoo and other websites. But again, all of them are adjusted for stock splits, and the adjusted close is also adjusted for dividend. So it is assumed that the dividends are reinvested immediately. This is also called the total return. And this is quite important to understand the difference, because you will use one of these to calculate, for example, valuation ratios. But this one here, the adjusted close, which is adjusted for both stock splits and dividends that are assumed to be reinvested immediately, this is what you want to use when calculating stock returns to an investor, especially over long periods, because the reinvestment of dividends can add several percentage points to each year's investment returns. So that's important to understand this distinction. And again, if you want to look up the data for a specific ticker, for example, Microsoft, it's very easy to do by just writing this command here, and we can also plot it very easily. By default, we use a name or shortcut all uppercase share price as a synonym for the daily closing price. So in all of these tutorials, when you see this share price, it is really the daily closing price. And we use the shortcut total return as a synonym for the adjusted close, which is again the daily closing share price adjusted for both stock splits and reinvestment of dividends, which is the total return you would get as an investor. And these two are only the same if the company has never paid any dividends. Otherwise, you will see them diverge more and more over time. And that is why it is important that you calculate investor returns from the total return, and you use the closing share price to calculate, for example, PE ratios and price to sales ratios and so on. Here you see the blue line is the total return, and the share price is the yellow line. And over time, they diverge more and more because of this reinvestment of dividends. In this case, they have both been normalized to start at 1 to show this. Then there are other data sets, for example, one here for loading company details. So this tells you for each ticker what is its SIMFIN ID, which is a unique ID in the SIMFIN database, the name of the company, and the industry it is operating in. And we can also load a data set with a list of industries, and it looks like this. So the industry ID, the sector, and the industry. So when you load a data set, you can also set the market that you are interested in. Currently, the SIMFIN database has quite a lot of data for United States, several thousand companies. It is only beginning with the German market, and there's a tiny bit of data for Canada and Singapore and different other companies, but that is probably not going to be public just yet. Over time, this is of course supposed to grow, and that is again why it is important for you to support this project. If you actually use the data, then pay a monthly, very cheap subscription so that over time this database will grow. It is actually a really big job to develop all of this. And there's another data set if we want the details for the markets. So this shows us the market ID, which is the two letters, for example, DE for Germany or US for United States, and then the name of the market and the currency they are using. I have written a longer explanation of some limitations about these markets. This has to do with foreign companies that have stocks trading on an exchange in another country. What currency should that be? In order to make the SIMFIN database very easy to work with, we have made some limitations so that we are only taking the stocks from the native market of the company. For example, if Coca-Cola is trading on 10 stock markets all over the world in different currencies, we only have it in its native US market. Okay, so what happens if you make a request to the server that it cannot fulfill for some reason? Then it raises an exception. For example, like this. If you want to download the dataset called Gray's Sports Almanac, unfortunately, this does not exist on the server, so you get this exception here. This could also be an exception saying that the dataset does actually exist, but you need to provide a valid API key in order to access that data. There are also a few helper functions which can give you more information about the datasets and their data columns. One is called info datasets, and if you call it without any arguments, it will just list all of the available datasets. This is basically the same as going over here on the Symfin website and getting the list of datasets here. But for some users, this might be practical to do using Python code. If you give it an argument with the exact name of a dataset, it gives you the details of the possible variants and markets and which columns are in this dataset. And the other function is called info columns, and there you can give it the name of a column. And we can use the Python shortcuts or these variables or constants, for example, company name, and it prints all of the details for that data column, whether it requires a premium subscription, which datasets it appears in, and a description of what it is. This function is also very useful because it can be used to search for example, if you know it's named something like shares, then it can print all of the columns that has this string in either the name or the shortcut or the description. There is actually another way to do this. If we go over to the web page with the documentation, we can type it in the quick search box down here, shares, and we get the same information. Let's go back to the tutorial. And the last half of the first tutorial is a general pandas introduction. If you're new to pandas, I would strongly recommend that you go through this. Spend the time reading through it, playing with the code. Personally, I'm not a super fan of pandas. A lot of things in pandas are really weird because the semantics can change dramatically if you change the arguments to a function in pandas, and the function may not be documented very well. And if you open the source code to look at it, it might be a file with 10,000 lines of spaghetti code with very little documentation. So pandas can be really difficult to learn how to use correctly. And even the people who are maintaining it are sometimes confused when you go on GitHub and you look what they're writing about various problems in pandas. So let's look at the next tutorial on resampling. And this is a very important operation because, for example, if you want to calculate price to earnings ratios, you have a daily share price, but you have 4 data points per year for the trailing 12-month data for income statements or balance sheets or cash flow statements or whatever it is you want to use. So how do we get these 4 data points per year to be the same as the daily share prices? So we can use both of these in calculations. That is what resampling does. There are basically 3 kinds. The simplest is called asfrig. I don't think I have used it for anything in any of my work with this. Normally, you would either use the more advanced resample function because this allows more advanced interpolation when filling in the missing values for upsampling, and it also allows more advanced summarization methods when you are downsampling. Then there is reindexing, which conforms a data frame to the index of another data frame, and this can also do some more advanced interpolation when you are upsampling. So this tutorial has a longer explanation of how you actually do this in pandas and what are the pros and cons and some of the pitfalls of doing it. And if you're not already familiar with how to do this, I strongly recommend that you read this tutorial in great detail. But I will just take the basic points here. So let's look at the resample function. And for example, if we have annual income statements and we take it for the single company Microsoft, then we can resample it to daily data points and we can use forward filling. And when we plot it, it looks like this. So it only has 1 data point per year, and then it inserts new data every single day, but it doesn't know what that data is supposed to be. So it uses a forward fill with the last known data. That is why you see in this plot that we have sort of like a staircase that goes up and down, because it just uses the last known data point from the annual income statements. That is forward filling. We can also use linear interpolation simply by calling this function here instead of forward fill. This draws a straight line between every 2 successive points, for example here and here, straight line up to here, so on. This is a form of cheating because it is using future data. It is using this data point here to generate all of the data points here. It doesn't matter so much if it's almost a horizontal line, but up here, for example, we have the future data point here that is used to calculate all of these data points here. This is clearly cheating. This is still useful in some kinds of statistical analysis, but if you want to make a trading strategy, this is cheating. You shouldn't do it. You should always use forward fill to use the last known data points. Resampling can also be used to downsample the data. For example, if we take the daily share prices for Microsoft, then we downsample it to monthly data points instead using the average. And if we plot it, it looks like this, which is more smooth than it would be if we had all of the daily data points. Now it becomes tricky because we have what is called a multi-index. We are indexing our data frames based on the ticker and a date. For example, for income statements, we are indexing by the ticker and the report date. For share prices, we're indexing by the ticker and the daily date. This is not supported very well in pandas. And if you try it directly, it will raise an exception. The resample function does have an argument that is supposed to work, but it doesn't work for upsampling. The way to get this working in pandas is to use what is called a group by statement. And this is explained very carefully in the last half of the first tutorial. And this is one of the things you really need to understand, because by default, pandas does not respect that we have separated our data between tickers. It doesn't respect that when it does calculations. So if you resample a data frame that has data for more than one stock, in the region that has data for two different tickers, it will get that data mixed up. And the way to separate these calculations is to use the group by statement in pandas. This is a bit of a mess. And because of that, we have supplied a resample function in the Symfin package, which can either resample a data frame for a single stock or for multiple stocks with a multi-index. And that function looks like this. So it basically just takes the data frame that you want to resample, how you want to resample it, for example, to daily data points, and the method you want to use, for example, forward fill. And if we do that for the annual income statements for Microsoft, it looks like this. And we can also plot the result. And again, we have the staircase pattern because we're using forward filling. We can also use linear interpolation simply by changing this argument here, and then we get more smooth lines. But again, this would be cheating if you want to use it in a trading strategy, because it uses future values to calculate the intermediate values. What you will often see that I do in these tutorials is that I use a plotting system called Seaborn, and it is abbreviated by SNS typically. And this allows you to define what you want to plot from a data frame. So here we can say that the x-axis should be the report date, the y-axis should be the revenue, and the hue or the color of the line should be the ticker. This is an incredibly easy way of plotting data for multiple stocks in a single plot, using just one line of Python code. So here we have the blue line for Apple, the yellow line for Amazon, and the green line for Microsoft for their revenue for a given report date. Now the resample method in the Symfin package also allows you to provide your own resampling method. And this is a little more advanced, I guess. I won't explain this in detail here, but for example, if you want to do quadratic interpolation, you can make a function like this. And then you get even more smooth lines. But again, this is even more cheating because it uses even more future data points. But for some kind of analysis, this might be useful. So now let's discuss reindexing. Because if you're using resampling, you say, I have, for example, quarterly data points and I want daily data points. You cannot say that you want the same daily data points as the share prices. This you have to use reindexing for. And again, what I have written here is a long explanation of how you should do that using pandas directly, and what are the pros and cons and some of the pitfalls. But it's not easy, and especially when you get to the multi-index, it becomes quite difficult. And here you see an example of that. By default, it doesn't respect the different tickers. It creates messed up data. So it gets a little complicated if we have multiple tickers. And for that reason, we have also made a helper function in the Symfin package for doing reindexing. So it takes the source data frame as an argument and the target data frame. So we want, in this example here, we want to take the income statements and use the index for the share prices. And we want it to respect the grouping by the ticker. and we want to use the forward fill method to fill in the empty data points. So this is super easy to use, and it works whether the data frames have one stock or multiple stocks. And in this example, the result looks like this. So we have taken the annual revenue and net income, and we have reindexed it so it gets the same data points for the same dates as the daily share prices. Remember, this is not every single day because weekends and holidays are not trading dates, so there are no data points for that. And that is one of the things that makes this reindexing slightly tricky. And if we use forward filling in the reindexing, it looks something like this. Again, a staircase pattern because we are using the last known data points for an entire year. But you can also do linear interpolation simply by changing this argument here, and then you get more smooth lines for the reindexed data. So let's go to the next tutorial. This is about growth and returns. And the way you do this in pandas is to use shifting of the data. So it's very similar. But again, there are many pitfalls in how to do this in pandas. And I give a long explanation of that with detailed examples. And I won't go through that now. But again, if you want to understand how pandas really works, then I recommend that you read this carefully. But to make it a lot easier for the end user, we have made a helper function in the Symfin package called relative change or rel change, which is specialized for calculating changes over time for this kind of financial data. This also supports data frames that only have one stock or multiple stocks. So again, you don't have these problems with having to use the group by functionality in pandas, because the Symfin helper function takes care of all that. So for example, this is how we calculate daily stock returns from the previous day until today. We first give it the data frame with the stock prices for Microsoft. Then we say that the frequency of this data is business days. Then we say that we want the relative change for one business day. And we set the keyword argument future to false, which means we want the past change from the previous day until today. And then we get this result here. So this is super easy to use. And for example, if we want the future stock return instead, we just change this single argument here, set future to true. We can use an arbitrary time interval. For example, we take the same data frame as before, and again we say that the frequency is the same for the original data. These are business days or trading days. But now let's say that we want to calculate the stock return 1 year into the future. So we set the argument here, years equals 1 and future equals true. And then we get the 1 year stock returns for Microsoft. So from this date, going 1 year forward, it returned about 18.5%. And with the reinvestment of dividends, that is the total return, it was about 20%. You could also say, for example, you're interested in 1 year and 3 business days. You simply add more arguments to this function here. If you want to calculate stock returns for multiple years, for example, let's say 3 years, then it is often useful to calculate the annualized returns. And you do this simply by passing this argument here, setting annualized to true. And once again, you can add different periods. So we can say we need the stock returns for 2 business days plus 3 weeks plus 3 months plus 3 years. And the function takes care of all of that. And it still calculates the annualized return correctly. And in the examples we just saw, we only did it for a single stock. But this helper function can also do it for data frames that have multiple stocks, and it does it correctly. You simply pass in that data frame and everything works the same. So you see this has calculated the stock returns for both Apple and Microsoft and so on. The exact same function can be used to calculate growth rates, for example, sales growth or earnings growth. The key to doing that is that you pass in the data that you want to calculate the growth rates for. In this example, we will use quarterly income statements. Then we pass the argument that the frequency of this data is quarterly. And then we say we want to calculate the relative change for 1 quarter. We want the past growth rate, so from the previous quarter to the current. But if you want the future growth rates, you just set this argument to true instead. But the result we get, we see it down here. And these are the quarterly growth rates for the revenue and net income. If instead you want to calculate the growth over an entire year, so this would be year-over-year growth in the quarterly revenue and net income, you have the exact same function call, but you just pass in the argument years equals 1 instead of quarters equals 1. So now you can see that from this period here until this period here, it grew the quarterly revenue of about 22% and the net income grew about 48%. Once again, you can do this for multiple years, and then it often makes sense to calculate the annualized growth rates. So we pass in the keyword annualized equals true. And again, we can calculate the exact same thing for data frames that have multiple stocks instead of just one, simply by passing in that data frame, and then the helper function takes care of the rest. The SymFin package also provides another function called mean log change, which is used to calculate the average change over many periods. You use this to calculate, for example, the stock returns for all, let's say, 1 to 3 year periods. And we will use this in other tutorials when we are studying the relation between predictor variables, such as price to earnings ratios, and average stock returns over the following 1 to 3 years. The reason that we're calculating the mean log change instead of just the mean change or the mean stock return or mean growth rate is that when it is implemented using pandas and NumPy, using vectorized computations, it is much easier to do that with the log change than the normal change or the normal growth rates. And this tutorial also explains the math behind all of this, but I won't go through that now in this video here. But for example, if we want to calculate the mean log change or the mean log stock returns over all 1 to 3 year periods, we do it using this function called here. So we have the data frame that we're interested in, the frequency of that data frame, which is business days or trading days. We are interested in future stock returns. We want them to be annualized, and the minimum period is 1 year and the maximum is 3 years. So that's all you need to call in order to calculate the mean log stock returns for all 1 to 3 year periods. This is an incredibly useful function. So let's go to the next tutorial, and this is about what I call signals. This is price signals and valuation ratios and financial fundamental ratios and so on. This tutorial explains how to do that correctly, because once again, this is not trivial in pandas. The SymFin package has a couple of helper functions for calculating standard signals. For example, price to earnings ratios, return on assets, return on equity, and so on. What I suggest you do is you use those examples and modify them for the signals that you are interested in. It would take me probably half an hour just to go through this tutorial, so you're gonna have to read through this yourself. So let's go to the next tutorial, which is what I call data hubs. This is what you would normally use to load data and do the signal calculations. If the SymFin helper functions already calculate the signals you're interested in, then this is all you need to use. The idea with a data hub is that it gathers together all of the functionality for loading data and for calculating signals and stock returns. It makes it a lot easier because you don't have to understand very much about how it works, and you don't have to make sure that you load the correct data and pass it to the correct functions with the correct arguments. The data hub takes care of all of that for you. So let's see a few examples of how to use this. So first we have to say what we are interested in. We are interested in the US stock market. Because we want to do all of these calculations very quickly, we are only interested in these 3 stocks, Apple, Amazon, and Microsoft. But if you set this to none or simply don't pass this argument to the stock hub when you create it, it will just use all the tickers in the dataset. Then we add an offset to all of the fundamental data, in this case 60 days. So when we are calculating valuation ratios such as price to earnings ratios, we want to shift that data 60 days to simulate that there is a delay between the report date and the date it was actually made public. Then we say that we want to refresh the fundamental data sets every 30 days, so that if the data files you have on your disk are more than 30 days old, it automatically downloads new data from the SymFin server. But for the share prices, we want to refresh those every 10 days. So then we create a data hub or a stock hub object with all of these settings. And this is now ready to download and load data, calculate signals, and whatever we want to do. For example, if we want to load share prices, we call the load share prices function from this hub object, and we give it the variant daily. We don't give it the market because that was set when we created the stock hub. And then we get this data frame here, and if it has it on disk and it is fresh enough, it will just load the data from disk. Otherwise, it will load it from the SymFin server, save it to disk, and then load it in this data frame you see right here. And you can see that if we already have it on disk, then it takes about 15 seconds to load it. But if we call this load share prices function from the hub object again, then because it uses a RAM cache as well, it can return the data frame almost immediately. We don't have to wait another 15 seconds. This also means that the data frames that the Stock Hub returns, you must never ever modify them, because even the internal functions for calculating signals will then use the data that you have modified. So if you by accident modify the data frame that it returns, then you just have to create a new Stock Hub object and start over. So we can also use the Stock Hub to calculate the signals like price to earnings ratios, return on equity, and so on. For example, if we call this function here FinSignals, give it the variant daily, then it calculates daily financial signals for the 3 stocks that we listed when we created the Stock Hub. And this gives us a data frame that looks like this. It has the current ratio, debt ratio, gross profit margin, net profit margin, return on assets, and so on. And this is for daily data points, so this has been re-indexed or upsampled from the 4 data points in the trailing 12-month data to something like 252 data points per year for all of the trading days. If you look at this text that gets printed when we call this function, you can see that it automatically loads the data sets that it needs to perform these calculations. It has already loaded the share prices and income statements and whatever. So those are not loaded again. They're just taken from the RAM cache. But then we see this line here that it says a cache file named the name of the function and then a strange code here, .pickle. It does not exist on disk. So, because it does not exist, it runs the function and calculates the pandas data frame that you see down here. Then it saves that data frame to disk so that the next time you call this function here with the settings for the Stock Hub and the variant daily here, then it will take all of these configuration settings, turn that into the key that you see here, and say, oh, there's a cache file on disk, and the cache file on disk is newer than all of the data sets that I'm using to calculate these signals, so I can just load the cache file instead of calculating it again. It doesn't matter when we only do the calculation for 3 stocks, but when you have 2,000 stocks, it takes a few minutes to do these calculations, whereas it only takes a few seconds to load the cache file. So that is why it is extremely convenient to use this disk cache as well. But everything is handled automatically by the Stock Hub, so you don't have to worry about anything. It should automatically make sure that you have fresh data. It also calls the function again, creates a new cache file, and so on. And we can also take a quick look at valuation signals. So this is like PE ratios and price to sales ratios and so on. You just call this function here, val signals. If we're only interested in the signals for the latest days, instead of calculating it for all days, we just give it this variant here, latest. And the result is this data frame here. So we have dividend yield, earnings yields, market cap, price to book ratio, price to earnings ratio. And of course, if you want it for daily data instead, you just call the same function with the variant daily. And the result is this data frame here, where it has it for the daily data points. So it is super easy to calculate the signals when you're using the Stock Hub. So the only question is whether these built-in functions calculate the signals that you are interested in. Otherwise, you would have to customize them to do what you want them to do. Similarly, the Stock Hub also provides functions for calculating stock returns. You simply call the hub object and this returns method, and you pass arguments for the investment period you are interested in, whether it should be future returns or past returns, and whether it should be annualized. So this automatically loads the data it needs from disk, or if you don't have it, or if it's not fresh enough, it downloads it from the Symfin server first, then it does the calculations, then it saves the result to a cache file on disk, so it can be loaded very quickly the next time, and then it returns the result to you. And for example, for Apple, it looks like this if we plot it. And we can also calculate the mean log stock returns, for example, for all investment periods between 1 year and 3 years. And it's just this one function call, and it does the same, loads the data, downloads it if you don't have it or if it's not fresh enough, calls the function, saves the result to a cache file on disk, and returns the result to you. So we can plot the 1 to 3 year stock returns for Apple, and it looks like this. Okay, so now you understand all of the basics of how Symfin works, and normally you would just use a Stock Hub because it gives you everything you need. So let's look at a simple application, a stock screener. And we start by creating a Stock Hub. We are interested in US stock market. We want the fundamental data to be refreshed every 30 days, and the share prices should be refreshed every day. Then we calculate all of the signals and put them into separate data frames. So here we have the financial signals. And because it's a stock screener, we are only interested in the latest data points. So we can save a lot of computation time by setting the variant to latest. And then we get this data frame here for each ticker and the latest date. We have the current ratio, debt ratio, gross profit margin, and so on, all of these numbers. We can also calculate these signals using 2-year averages so that it smoothens out, for example, the net profit margin for the last 2 years instead of just for the last year. And we get a data frame that looks almost the same. It has just more smooth data. Similarly, we calculate a data frame with growth signals. Again, we use a stock hub and this simple call here to get the latest data points. And it looks like this. So we have earnings growth, free cash flow growth, sales growth, and so on. Once again, when we call the function in the stock hub, we can pass a function for calculating 2-year averages. So we get more smooth data points. And then we get a data frame that looks like this, almost the same, just more smooth data. Then we calculate the valuation signals much the same way. We just call this function in the stock hub and say we want the latest variant. And we get this data frame here. Now we have for each ticker the dividend yield, earnings yield, market cap, price to book ratio, price to earnings ratio, and so on. And once again, we can call the function with this extra function argument here to use, for example, 2-year earnings or 2-year sales instead of just the last year's earnings or sales. So we get more smooth data points when calculating all of these valuation ratios and signals. Now that we have calculated all of our signals, we combine them into a single data frame using this pandas code here. So now we have one big pandas data frame with all of our signals. And we do the same for the signals that had used 2-year averages for smoothing the data. So this is an example of a net screener, and this is an idea that was invented by a man named Ben Graham, and he was a teacher of Warren Buffett. It is basically trying to find companies that are trading at a share price that is lower than a conservative estimate of the company's liquidation value. That is called the price to net ratio. And when it is between 0 and 1, it indicates that the stocks are trading at a discount to the estimated liquidation value. If you go back to the financial crisis in 2009, there were actually quite a lot of companies that became so cheap that you could buy them at a discount to their estimated liquidation value. In regular times, it is not so common, and it is typically because the company has some kind of problem and shareholders believe that they are going to burn through all of their cash before they fix their problems. But let's try and make a screener that can detect stocks that are trading at net discounts. So what we do is we create a Boolean mask from the signal for the price to net ratio, which must be greater than 0 and it must be less than 1. Then we get this pandas data frame or pandas series here, where for each ticker at each date, we have a Boolean whether it is trading at a net discount. So for all of these first tickers, it's all of them are false. So these are not trading at net discounts. But if we use this Boolean mask we have just created to look up which rows in the signals data frame actually satisfy this condition, then we get this list here. So we can see ticker Adil on this date here traded at about half of its estimated liquidation value. And we have a whole list of them here. So let's try and make another stock screener where we have multiple criteria. First, we say that the market cap must be greater than $1 billion. And the way we add criteria is that we simply create new Boolean masks and we AND them together. So first, we create a mask for the current ratio to be greater than 2. And we take the logical AND with the existing mask we have already. Then we create a new Boolean mask for the debt ratio where it is less than 0.5. And we AND that together with our Boolean mask, and so on and so forth. We can also use some of the signals that were calculated using 2-year averages. For example, the price to earnings ratio using the average earnings for 2 years, or the price to free cash flow using the average free cash flow from the last 2 years, and so on. And again, we just AND all of these Boolean masks together. And finally, we apply that mask on the signals data frame so that now we can see which of the tickers satisfy all of these conditions. In this case, there's actually only 5 companies that satisfy the conditions that we have made. This ticker here, here, and here. We can show this data in different ways. For example, we can select a subset of all of the signals we want to show, and we can sort it, for example, according to the price to free cash flow ratio. So we start with the lowest one for this ticker here, and it increases. So that was an example of a basic application using SimFin data. It was very easy to make a stock screener. It is just as easy to do statistical analysis. I won't go through this tutorial, but I will just say that what is being done in this fairly easy tutorial is basically the same that almost all finance professors in the world are doing. It's one form or another of so-called regression analysis, and that's basically almost 100% of research papers in finance is basically just this. And if you read through this tutorial, you will be able to do the same. Let's go to the next tutorial on machine learning using scikit-learn. And I will also go through this fairly quickly, but it is actually not very difficult. So once again, we create a stock hub for loading all of the data that we need and for processing and calculating all of the signals, which we do here. Again, the financial signals, growth signals, valuation signals, we combine them. Then we have to clean up the data. First, we remove some missing data. Then we calculate 1 to 3 year stock returns. Again, this is just done using the stock hub, so it's very easy to do. Then we combine the signals and the stock returns into a single data frame so that the indices are being aligned. Then we clean the data some more. Then we split the data into training and test sets for doing the machine learning. And then we do the actual machine learning. First, we do it with a regression model. So we are trying to find the actual stock return as a real value. And here we have some parameters for scikit-learn's random forest model. And then we make an instance of that model. And then we fit it on our training data. And that takes about 4 minutes. And this has created a number of decision trees that look like this. So it's basically if then else statements. For example, if the price to free cash flow is less than or equal 5.57 and the net profit margin is less than or equal to 0.01 and so on and so forth, then it thinks that the output value or the stock return should be so and so much. And the random forest has 100 of these decision trees, and then it just averages the results to create an estimate of what it thinks that the stock return should be for given input signals. And if we take an example from the training set, so the blue one is the true data, and the yellow one is what the machine learning model, the random forest, has predicted. This is a quite good fit and looks like something we could use for a trading strategy. But wait a second, because this is what it looks like on a stock from the test set, which has not been used during the training of the model. Now it doesn't perform very well anymore. This means that the model was overfitted to the training data. So this tutorial shows you how to use scikit-learn. Now it is your job to do research to find out which signals actually have predictive power and which machine learning model is best and which parameters for that model is best. You can also do something called automated machine learning using, for example, a system called Teapot. And if you do that, I highly recommend that you make a GitHub repository. You tag it with the word SimFin so others can find it. And then you tell the rest of the world about your research. That is the idea with SimFin, that you can make research and share it very easily with other people, and they can download the data automatically when using the SimFin package. So that's my hope, that's my vision for why I made this API for SimFin. I have built the Python API, and another guy named Thomas has built the database. So let's just briefly look at the last tutorial, and this is about neural networks. It's basically the same as the last tutorial on machine learning using scikit-learn. This one just uses TensorFlow and Keras instead. I will just go through it very quickly. Once again, we start with the stock hub for loading the data and calculating the signals, which we do here and here and here and here. And then we combine it into one data frame. Then we clean up the data a little. Again, we calculate the stock returns for 1 to 3 year investment periods. We combine the signals and the returns. We clean the data some more. We split into training and test sets. Then we have to scale the signals because the neural network works best if the data is in a fairly small range, say between 0 and 1, or it has a mean of 0 and a standard deviation of 1 or something like that. If we have, for example, market caps that can take on values of either millions or billions, and then we have price to net ratios that are between 0 and 1. The neural network cannot handle this so well, so we first have to use a scaler to get all of the signals in a fairly narrow range. And then we can start building the neural network. Again, we have two examples. One is for doing regression, where we're trying to predict a real value. And we have another example, which I didn't show you for the machine learning, but we have that there as well, which is for doing classification. So just finding out whether it was a loss or a gain, but not exactly how much that was. But first we make a neural network for doing the regression, and we are using Keras to build this. So we start with an input layer, and then several hidden layers, and then finally an output layer. Then we compile that model, and then we can print it. And these are the arguments for training the model. So we want to use a batch size of this much and 40 epochs, and we also want to use a validation set so that we can see during the training how it performs on data that it has not seen during that training. And when we run it, it takes a minute or two on a normal computer. It looks like this. So we just give it the training data, and we can plot the training progress. So this shows the mean absolute error. For the blue line, it is for the training set, and for the yellow line, it is for the validation set. And this is supposed to be minimized, which is also what happens on the training set. But we see the performance on the validation set is very bad. So it means that the model is overfitting more and more to the training data, and it does not learn how to generalize to data that it has not seen before. We can also show an example like this. So for one of the tickers in the training set, it has learned to fit it quite well. But here's an example from the test set where it performs really badly. So once again, this tutorial has shown you how to use the Symfin data and API with TensorFlow and Keras. Now it is your job to find out which signals actually work and which design for the neural network gives good performance. And then you can share that research if you want. I hope you will share some of your research with the world, and you do that simply by making a notebook like I have made here and put that on GitHub, tag the repository with the keyword Symfin so others can find it. And then everybody can download that notebook and run the exact same experiment with the free datasets. And if they want to run it with a fresh, full dataset, they simply pay a fairly cheap monthly subscription. So I hope a lot of people will be using this so we can revolutionize our understanding of finance. I wish you all the best.